So this one guy once, walked up to me on the street and he said, "Here's a list of numbers, son. I want you to tell me what's going to come next." And I said, well, I don't know. I haven't yet done chapter 5 in Mr. Robinson's algebra class. And he's like, "Son, you got like 10 seconds or else I'm going to fail you." And they were like, "No." And so then we're like, okay, let's quickly figure out the pattern. So there are numbers here are consecutive, and the -3 comes after the -7 and the 1 and the 5. Ooh, 5 and 1 and 9. Ooh, something looks good here. These are confusing, but I get these ones. It looks like +4. Yeah, +4. And are these +4 too? Yeah, it looks like here. When I look at this, there's a pattern. Every time, sir, guy on the street who's trying to fail me, even though I haven't yet taken Mr. Robinson's chapter 5 unit, I still know what to do. I add 4. And he's like, "Good job, son. That's called an arithmetic sequence." And we were like, whoa. And it was so cool. And then he took this one out, and we were like, oh, I don't really know too much about this one. Even if I could add and figure this one out, I don't think it's plus what? Plus 48? Ooh, that's 48. This one here is plus 12. Plus 5? Plus 3? I don't even know what they're. But these ones, too, it looks like there's even something here. Look at that, where it's plus. So you start to get stuck. You're like, well, it looks like it's not an arithmetic sequence like that other one that guy says. Maybe you have to try something else. And I'm like, well, I'm still kind of bad at math. It looks like, I know what this one, if I divide by 4, I'm well versed in that. Same with this one here, dividing by 4. Yeah. And yeah. You're dividing by 4. He's like, what's that the same as multiplying by? And I'm like, well, if I take a quarter and I divide it by 4, then I get 25 cents. That is a quarter, literally. And that must be multiplying by a quarter, which is 1/4. He's like, that's right, son. Nice job. I don't know why he calls you son. And he's like, that's a geometric sequence. And you're like, okay. And then he takes out this one, and you said, I'm done. He says, that's okay. That's called quadratic. We'll get to that later if we must, but let me give you this one, son. He's like, I already know this one. +2. Give me a harder one. That's arithmetic. And he's like, you're right. Okay, I won't fail you, he says. And that was it. And there's your teaser. It's like your opening scene to like a horror film where they first show that grisly murder, and then they like, here's the title sequence, and then they show you the rest of it. Or they show you it again, which is what I'm going to do. So here's the chapter 5 review. Contains closure assignment problems plus 2 extra word problems. Looking through, now I haven't done the closure assignment yet, but looking through it, I noticed not everything is sequences, obviously, but it's good to also get some other review involved in it as well. What I'm going to do is, based on this, I actually am going to revisit this problem because we're going to come up with equations for them, just so you get a little more. But what I'm going to do is look over some key terms here. I'm not going to do too much on the screen because I want to use the examples to help accentuate what these things say. But these are words I'm going to use, okay? So starting with the word sequence, it's the big word in this chapter, and a sequence is just a list of numbers. So the A through D problems that you just saw, those were all sequences. They all had a pattern involved in it, and one of them actually was a quadratic one, but these ones that we're mostly going to be focused on when we make equations will be separated by some sort of common difference, which will be an arithmetic sequence that you just saw, or a common ratio, which is a geometric sequence, and we also saw one of those. The thing about sequences, though, compared to something like a linear function where you have f of x equals something, or y equals mx plus b, anything like that, like 2x minus 7. The difference between this and when we use this notation here is regarding the domain right here. Whereas in the first example right here, the domain for x is all real numbers. And what I mean by that is you can substitute any value for x literally, and you will get a value out for y, or for f of x. That's true here as well. The difference is, though, in a sequence, the list of numbers is already pre-filled out. You know, it's already predetermined. And the first term is at n equals 1. And the second term is at n equals 2. And the third term is at n equals 3. And the 100th term is at n equals 100. And there is no term 0 in the sequence. There is no term negative 20 in the sequence. There is no term 3.5 in the sequence. There are only numbers that look like this. They're called counting numbers. And they go on and on. Whereas in this example with the function, you can substitute anything for x and it will apply to your graph. So that's the difference between these two, and that's otherwise sequences kind of look the same. The only other thing is we use recursive form in sequences, which I'll get to in a bit. Okay, now we are using new letters though for this assignment, so that way we separate it from this. Now n refers to the term number, t of n refers to the value to which you're referring, and then in an arithmetic sequence you get something called a common difference. We just saw some of them on that other page. We saw a common difference of when you're adding 4 over and over, and a common difference of when you're adding 2 over and over. It's the difference between any two consecutive values in a sequence. So if we look at the list that had 0, 2, I mean, I guess we're going to do this one later anyway. This list would have kept going on like this, obviously. To find the common difference, I mean, you can look at it sometimes and say, well, when I know, I know. But to figure out how much you're adding to get from one value to the next, take the bigger value and subtract the value before it. 8 minus 6, 6 minus 4, 4 minus 2, and 2 minus 0 should all give you the same common difference of 2. And that's what's true in an arithmetic sequence. Now your common difference can also be negative, which means your list would be decreasing. The values would be decreasing in your list as it went on. A common ratio is something in a geometric sequence. So what happens instead of adding or subtracting, you multiply and divide. And that's where the ratio thing comes into play. So if you have, I forget what it was, I think negative 64, negative 16, negative 4, negative 1. Obviously, we're kind of doing some of these beforehand. This common ratio here, what you're going to ask yourself is, what am I multiplying? We said, what are we dividing by? You also, it's probably better to figure out what you're multiplying by. What are you multiplying by from one term to the next? Well, to do it, take the value of one term, divide it by the one before it. So, common ratio, I can do negative 16 divided by negative 64. That should be the same as negative 4 divided by negative 16. Negative 1 divided by negative 4, which you should know that one is positive 1 over 4. So that's your common ratio. So you can do this in one of two ways. They can either tell you what kind of sequence it is, and then you figure out what kind of ratio it is, or they might ask you to figure out if it is even a sequence or whatever, and you're going to run some tests. And sometimes you can see it straight up, but sometimes it takes you a second to determine what it might be. Okay, when it comes to this notation right here for explicit form, for arithmetic and geometric sequence, what's going to happen is you are going to use the term's position to find its value. Meaning, if I try to look for term number 100, that 100 is actually being calculated somewhere in my formula. T of 100 would make 100 equal to n, or n equals 100, and you substitute 100 for n in the equation. So it's actually used. I'm not going to talk about the formula too much here. Same with this one. I'll just talk about it when we arrive at them. Same with geometric sequence though. This n, if I wanted to find the 100th term in a geometric sequence, I would actually substitute the number 100 into the equation and use the rest. Confusing as all this looks, hopefully it'll be a little cleared up by the end. Recursive form is completely different compared to the other ones. This one is actually slope-intercept form right here. This one right here is something that you've never seen before, and it's not a slope-intercept form. Although, I do bet that you can say this thing in plain English better than even you can do the math. What did we do from 0 to 4, 6, 8? You add 2. You add 2 from what? The number before it. That's what this thing's saying right here. This says, to find the value of the term after this one, you take that previous term and you add the common difference. If I want to find out the next term in this list after 8, which would be, this is the first term, second, third, fourth, and fifth. If I wanted to find t of 6, the sixth term, I take t of 5, which is the fifth term, which is 8, and I'm going to add the common difference of 2 to it. 8 plus 2 is 10. So t of 6 would give me 10. So that's what this notation means. You understand the English portion of it. I hope you understand the math portion of it. In a geometric sequence, it's the same thing, only you take the previous term and you multiply by the common ratio to get the next one. If I want to figure out what the next term is in this sequence, what the fifth term, I guess, is, I'll take the fourth term, which is -1, and I'll multiply by its common ratio of 1/4. That would give me -1/4 as my fifth term. So that's the idea behind it. I don't want to do more on this page. I want to actually do some practice problems, and from there we'll make things happen. Maybe I go back to say how these formulas actually come to be. I think the recursive ones make complete sense. These ones are more of, do I memorize it? What do I do with it? Right? So we'll see what we can do. Okay, so I'm going back to these problems again. Now, I will coin what kind of sequence it was, and we're going to talk about how to come up with an equation for them, whether it's recursive or explicit. C, I will probably do a little more ignoring for. However, we can still come up with equations for that as well. Okay, so A was an arithmetic sequence. It had a common difference of 4. Now, its first term is -7. I did say there was no 0 term. What I mean is, in the sequence, there is no 0 term. You can make up a term 0, though, if you follow the same pattern. You can make up a term -1 as well. If you're adding 4 each time, and you added 4 to get -7, term 0 would have been -11. This guy right here. Now, why is term 0 important? For your equation. And here's why. If you want to use explicit form, and you want to solve for the value at term n, and you want to use n in your equation, here's what the original equation looked like, and it had t of 0. Here's what it actually says if I rewrite it. To find the value of the nth term, I'm going to have a base value to start from, and I want to add the common difference this many times. Remember, dn is d times n. d is the common difference, n is the term number. If I want to find term number 1, I want to take my base value here of -11, and I want to add my common difference 1 time. Notice how d is 4, that substitutes, and t is 0, etc. But n is 1. This number will say how many times I'm going to add the number 4. Okay, when I add it once, I get -7. If I start from -11 and I add it, I'll just skip ahead to 4. If I add it 4 times, I will get the fourth term. Okay, so from -11, 1, 2, 3, 4. And that equals 5, as this equaled -7. So as you can see, I actually use the term position, and I actually calculate with it to figure out what to do next. Now, you don't have to write it in this way, but this helps make sense of what the equation is. I think the reason they do it this way is because this looks a lot like y equals mx plus b. Okay, otherwise, this one makes a little more sense in terms of what's actually happening. And if you want to find term 100, what do? You start from -11, and you're going to add 4 100 times. Now, it would be silly to do it right here and just add like that. That's why you do 4 times 100. Adding 4 100 times is the number 400. And 400 minus 11 is 389. So you can keep going with that. All right. But in general, your equation, as I write one more time here, is t of n equals 4n minus 11. This is in the other order. So that's the general explicit form equation for that. The recursive form would look as follows, and I'm not going to say too much about it. I'm just going to write the equation. To find the value of the next term, you take the value of the previous term, and you add the common difference of 4. And you want to give them some sort of value to reference, because you say, okay, great, I'm going to add 4. From what? So you want to give them something. Whatever term you have, you can give them term 1, term 2, 3, 4, or 5, or 0, or 19. It doesn't matter. I'm going to give you term number 1, though. There you are. So there's a lot to do with A there. Let's go on to B. Okay, this is a geometric sequence. So in a geometric sequence, we have a common ratio, and we talked about what it was before. It was 1/4. You might say divide by 4. Ratio, though, in this case is saying what are you multiplying by? Dividing by 4 and multiplying by 1/4 are the same thing. So when it comes to the explicit form, you know what, let's do recursive form first. When it comes to the recursive form, to find the value of the next term, I want to take the value of the term before it, and I want to multiply by the common ratio. In this case, 1/4. Let's give ourselves a value to go off of. T of 1 will be -64. The value of the first term is -64. To find the value of the second term, take -64, multiply by 1/4, you get -16, so on and so forth. So on and 1/4. Okay, so if you multiply by 1/4 each time here, here's where things get a little confusing for multiple reasons. One, you're using exponents for this thing. Two, we're probably going to be using the value t of 1 more often than we'll be using the value t of 0 for this next case. And the reason is simple. When you do a lot of geometric sequences, your first term will more often than not be an integer, and your 0 term will more often than not either be a huge number or be a fraction. In this case, it'll just be a huge number. Your term 0 will be -256, and it's not unreasonable. But what happens if you're using term number 1? Remember, term number 1 is 64. Term number 2 is -16. If I want to find the second term, I'm going to take term number 1 and multiply it by 1/4 once. So here comes the issue. The second term is t of 2, the value of the second term. So if I want to find the value of the second term, I'm going to take the first term, multiply it by this common ratio. I'm only going to do it one time. So the question is, but wait, n is 2. How do I do this? I'm going to take 1 away from this number, 2 minus 1. Okay? And that gives me -64 times 1/4 to the first power, which is -64 times 1/4, which is -16. If I want to find the value of the fourth term here, -1, how many times do I multiply by 1/4 starting from here? Once, twice, 3 times. So to find the value of the fourth term, I'm multiplying by 1/4 3 times. I'm going to say this next part really quickly. Hopefully it just connects. To find the value of the fifth term, you're going to multiply by 1/4 4 times. To find the value of the sixth term, you're going to multiply by 1/4 5 times. To find the value of the seventh term, you're going to multiply by 1/4 6 times. To find the value of the eighth term, you're going to multiply by 1/4 7 times. To find the value of the ninth term, you're going to multiply by 1/4 8 times. Find the value of the 10th term, you're going to multiply by 1/4 9 times. As you can see, what happens is you are multiplying by 1/4, your common ratio, 1 time less than the term position that you are at. So if you wanted to find the value of the 100th term, starting from -64, you would multiply by 199 times, not 100 times. Now, if you do want to have an equation where you do multiply by 1/4 100 times, here you would have this equation instead. So, t of 0, the value of term 0, is 1 common ratio multiple less than the first term. This would be -256. Okay, you can figure what that one is. That's fine. But once you do this, look, fourth term, from here you multiply by 1/4 once, twice, 3 times, 4 times. Fourth term, 4 times. So this way it actually connects. Again, the problem with t of 0 here, -256 isn't bad. The problem is when you have fractions. So this is okay. This is okay as well. I'll probably be using this more often, but it depends on the problem type. Okay, so that's part B. Part C, it's a quadratic equation, and here's kind of where I'm going with this. Let's say you're trying to determine whether it's arithmetic or geometric. If it's arithmetic, it means it has a common difference, which means 0 minus 1 would be the same thing as 1 minus 0. That would be the same thing as 4 minus 1, and that would be the same thing as 9 minus 4. Well, as you can tell, negative 1 and 1 are not equal. Neither are 1 and 3 with negative 1, and neither is 5 with 3 with 1 or negative 1. These are not equal. This does not have a common difference. This is not an arithmetic sequence. Is it a geometric sequence? What would you test? I'd test to see if 0 divided by 1 was the same thing as 1 divided by 0, 4 divided by 1, and 9 divided by 4. Well, 0 over 1 is 0, 1 over 0 is undefined, so those two aren't equal. 4 divided by 1 is 4, and 9 divided by 4 is 2.25. Not the same thing, not a common ratio, therefore this is not geometric either. So at that point you can just say neither. This one's a quadratic equation, and what that means is you're taking your variable in some sense and you are squaring it. If I wanted to be very, very specific with what this would be, think about what happens if n equals 1. When n equals 1, you get your first term here. So it looks like you might be taking your term and squaring it, so it might be t of n equals just n squared. Let's check the second term. Is the second term 2 squared? No, it's 0 squared. Look, it goes to 1, then 0, then back to 1, much like a parabola, whereas term 0 would have been 4, and term negative 1 would have been 9. It has that pattern, so it's not really that you were squaring 1 in the beginning. You might have been squaring the number negative 1, because this could be 0 squared, then 1 squared, 2 squared, 3 squared. So the question is, how do you come up with an equation? Well, if you're squaring negative 1 in this case, then you've subtracted 2 from here to get there. And you subtracted 2 from 2 to get 0, and you subtract 2 from 3 to get 1, etc. So your equation, it's not this one, but it's going to look like this. Now, how much does this matter to you? Probably not any. So I wouldn't be too concerned about what you do with this specific problem. I won't get into the recursive formula for that, but there is an example of a quadratic form right there. Again, probably ignore that, but at least now you know that, hey, it's possible. Okay, D, I told you it's an arithmetic sequence, but some people out there might say, wait a second, couldn't this be geometric? Isn't 4 divided by 2, 2, and isn't, yeah, but then you try 2 divided by 0 and you get undefined. You take 0 and you multiply it by anything, doesn't matter what it is, you're going to get 0 back. So this cannot be geometric. Basically, a geometric sequence can't have 0. Okay, an arithmetic sequence, term number 1 is 0, 2 is 2, 3 is 4. Term number 0, the one before it, which will be important, is negative 2, because your common difference, as you can tell, is 2. So your equation will be t of n equals 2n minus 2. And at the sake of saving the whole explanation of why that is, if you can find your common difference in your term 0 and you understand the basis of the equation, you're good to go. A recursive equation would be taking the term before it and adding 2 to find this term here. So take the term before it and add 2, and we start from t of 1, which is 0. So there you go. Explicit and recursive form for all of those guys. With that, I will speed up doing more example problems. Okay, number 125. Find an equation to represent each table as a sequence. So, in this case, now you have the table. It's the same thing as something separated by commas. So I could list this sequence here as 4, 1, negative 2, dot, 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 dot. I could list this one as 6, 7.2, 8.64, dot, 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 dot. And because this is showing n as 1, 2, 3, 4, etc., then we are at the head of the sequence. We can also find the 0th term, which will be very important for this one, not as so for this one, but we will. As you can tell here, 1 minus 4 is negative 3, negative 2 minus 1 is negative 3. Looks like this is an arithmetic sequence, which means we found a common difference here of negative 3. Term 0 would be asking, if we're subtracting 3 this way, and we subtracted 3 to get 4, what was the term before it? And that was 7. So term 0 is 7. So your equation is t of n equals negative 3 n plus 7. And once again, n represents the term position. And in this case, in the equation, it represents how many times you'll be subtracting 3. from 7. The first term, you'll subtract 3 once. The second term, you'll subtract 3 twice. The third term, you'll subtract 3 times, etc. That's the explicit formula. The recursive version, to find the next term, you start from the term before, and you subtract 3. And term number 1 is 4. So you must specify what some term is. I can specify term number 3 is -2. That's okay. Whichever way you'd like. My 6 looks bad here. Okay, part B. You can check and see if it is an arithmetic sequence first. 7.2 minus 6 is 1.2. 8.64 minus 7.2 is 1.44. Doesn't look like it has a common difference, so it's not an arithmetic sequence. Let's wipe that out. Let's check geometric sequence. If it's not geometric sequence, don't worry about writing an equation. Let's see if 7.2 divided by 6 here is the same as 8.64 divided by 7.2. And you know what? I'm without a calculator tonight. I could go to the flip phone, but I'm going to make a heavy assumption that these are exactly as they're supposed to be. So this one, ooh, they want us to find the fourth term as well. I'll do that in a bit. 7.2 divided by 6, that is, oh gosh, I had this in my head before, 6 over 5. So that's 0.2. And this one, I imagine, is 1.2. Let's just say it is. If it's not, I'm sorry. So your common ratio is 1.2. That means, excuse me, that means you're multiplying by 1.2 each time here. If you want to find your term 0, be my guest. Here's the problem. You'd have to do 6 divided by 1.2 to figure out what it is. Oh, you know, actually that number's not bad. What is that? That's 5. Actually, that's still a pretty good number. So you can do term 0 and work with that. So, explicitly, I have one of two equations. I can either write it based on the first term. I take the number 6. I multiply by my common ratio 1.2, one time less than the term number that I'm looking at. Or I can write it where I start from the number 5, which is term 0, and I multiply by 1.2 exactly the same number of times as the term position that I'm looking for. As you can see, to get to 6, I multiply by 1.2 once. This is the first term, remember? This is the second term and third term. So to find the fourth term here, I want you to see why these two are the same thing, actually. I'm going to do this twice. I'm going to do the top one here. Take 6, multiply it by 1.2 to the 4 minus 1 power, which is 6 times 1.2 cubed, which is this. I have to go to my flip phone for this one, so let's do it. 6 times 1. Now, I don't have exponents on this. All the more reason to get a new phone. I know. 10.68. No rounding here. 10.368. Next time I do this, here, I'm going to do it with the second equation. And t of 4 equals 5 times 1.2 to the 4th power. To save time, this is also 10.368. Now the question is, why are these the same thing when these are two different looking equations? Because I want you to think of what exponent means. Exponent means how many times you're multiplying a number by itself. What's the difference between 5 and 6? You might say it's 1, but we're not looking for difference. We're looking for what is the ratio. This number is 1.2 times larger than this number, which means we multiply by 1.2 one more time here than we do here, because this already has one more multiple of 1.2 than this one does. If that explanation doesn't make sense, and I'm not sure if the exponentiation portion ever will, because that is truly what it means. So there's no difference there. Okay, that's the explicit form. Let's also get the recursive form for this. It's going to be pretty straightforward. To find the value of the next term, you take the value of the term before it, and you multiply it by 1.2, starting from 6. There you go. All set. Let's speed this up. Solve the following systems algebraically. Okay, so as you can tell, this isn't sequences anymore. Alright, but the show must go on, and I would like to do these a bunch of different ways, so you get a lot of different ways to do it. Okay, if you were to solve this algebraically, you have to find both x and y. In order to do that, you must get one equation by its you must get one variable by itself in an equation. So there are three different ways to do this. You may choose equal values method, which I'm actually probably going to do after my first one, substitution, or elimination. Okay. Equal values method means getting one variable by itself isolated in both equations. Now substitution just probably means doing it to one variable, which is why I'm probably going to do substitution first, and I'll do equal values method second. Okay, for substitution, like I said, get one variable isolated in at least one equation. Now there are three potential candidates for getting something by itself very easily, and normally the 2 wouldn't be troublesome to get it by itself. I'll show you as an example over here. This 2 would be just fine. The problem is when you're dividing by 2, you're dividing 1 by 2 and you're dividing 17 by 2, and you're coming up with fractions. There are a lot of different ways you can isolate this thing. I'm going to go ahead and isolate this x variable here because it looks like just adding this y over will be quick and painless, and it leaves me with positive numbers still. So in order to do that, I have to add both sides with y right here, and I'm going to get x equals 2 plus y, or y plus 2. Right? Now that I have it isolated, I can take 2 plus y and I can substitute it in for x in this equation. Okay, you have to do it in the other equation. So for substitution here, now we have the equation on top, 2 plus y plus 2y equals 17. And you solve for y. Y plus 2y is 3y. Y equals 15 when you subtract 2. 3y equals 15 when you subtract 2 and divide by 3, you'll get y equals 5. Okay, you solve for y. Now you have to solve for x. In order to do that, pretty straightforward because you already have an equation that you've made where x is by itself. So x equals 2 plus 5. So x equals 7. So your final answer there is this ordered pair 7, 5. And what this means is if you substitute 7 for x and 5 for y in both equations, you will make a true statement. And that's what we were going for. Okay, that's one form of substitution. We could have done that isolating any set of variables. Now let's do equal values method. Okay, I had isolated x in this equation previously. I'm going to do it one more time. Now let's go ahead and isolate x in this equation as well. By subtracting 2y over to this side, we'll get x equals 17 minus 2y. What equal values method says is if one variable equals two different sets of expressions, you can set them equal to each other to help solve for your unknown variable. Because x is the same x we're trying to refer to in both equations. So 17 minus 2y equals 2 plus y. If I add 2y over to this side, I'll get 3y. If I subtract 2 over to the other side, I'll get 15. And once again, you get back to where you were going. Y equals 5. Substitute, you get x equals 7, and you keep going. So equal values method is probably one more step. So if you already have one variable isolated, I suggest just use substitution. Probably good from there. Final one here is the elimination method. And what elimination method is all about is when separated by the equal sign here, you can add everything on the left side to here and everything on the right side to here because both sides of the equation are balanced. So you're not manipulating the equation into an unbalanced form. The problem with adding down the list here when you combine like terms is nothing cancels out. You'd end up with an equation that says 2x plus y equals 19. And as you know, the whole point of the whole idea of solving equations is to get one variable by itself in the equation. We don't have that yet. So we have options to do. Here are my two options. Eliminate y or eliminate x. Okay? Here are the ways I can do it. If I decide to take the bottom equation and multiply everything by -1, which means all terms on both sides, I will get this setup for both my equations. The top one stays as is. The bottom one, every sign changes. What does that allow me to do? When I add down, it allows me to cancel out x's. X minus x is 0. 2y plus y is 3y. That equals 15. And obviously we've seen this before. I don't have to keep going from there. Okay, you know what we'll get. The second way of doing this problem is eliminating, instead of eliminating x, let's eliminate y, because we haven't even done one where we've eliminated y first. Or I mean, where we've gotten x by itself. So if I take this equation and multiply it by 2, notice how with the top remaining the same, the bottom gives me this, because I multiply everything by 2. Now, as you add down the list, the y's cancel instead of the x's, and you get 3x equals 21, and you get x equals 7, which is what it's supposed to be as you get over here. You take that 7 and you substitute it either in this equation, this equation, this equation, or this, in any equation, and solve for y, you'll get y equals 5. I'm sure there, you could multiply the top by -1 to solve for y, all that. There are a lot of ways you can do it. I wouldn't have divided this by 2 though, because again, you'll come up with fractions. It takes a little long. Okay, here's one where I can still do substitution or elimination. In this one, I would probably not do equal values method. And the reason is because it would take a little too long to get one variable by itself, and I would come up with fractions. But let me show you how substitution still works out here. It's still very possible to do. Substitution, elimination. Okay, substitution method. Let's choose to get a variable by itself, either this one, this x, this y, this x, or this y. Now here's the thing you ask yourself. No, here's the thing you tell yourself. Eventually, if I solve for this x here, that means I'll have to divide by 4. And you ask yourself, can I divide 5 by 4? Can I divide 11 by 4 without getting a fraction? The answer is no. I would not try and eliminate this, or I would not try and get that x by itself. How about this y? If I solve for y, I'd have to divide by 5. Can I divide 4 by 5? Can I divide 11 by 5 and get an integer? No. So that y is out. How about this x? If I solve for x, I'd have to divide by 2. Can I divide by 6 by 2? Can I divide 16 by 2? Yes. So it looks like this x is in. This y, I have to divide by 6. Can I divide by 2 by 6 and 16 by 6? No. You can, you just will get fractions. So it looks like if I want to do substitution, this x is the one that I would want to isolate. Which means I'd have to subtract 6y from both sides, and I get the equation 2x equals 16 minus 6y. Divide by 2, like I said, you divide everything by 2. Keep in mind this negative right here, you're going to get x equals 8 minus 3y. So now you can use that 8 minus 3y, take it and substitute it in for x in the top equation, just like we did for substitution last time. This will take place of x, and it will say 4 times 8 minus 3y plus 5y equals 11. So you can see, as you can see, there's still work to be done. Distribute the 4 here, and you will get 4 times 8, which is 32. 4 times negative 3y, which is negative 12y. Plus 5y equals 11. Not much room here. Negative 12y plus 5y is negative 7y. So 32 minus 7y equals 11. If I subtract 32, I'll get negative 7y equals negative 21. Divide by negative 7, you will get y equals positive 3. Now you're still not done. You have to solve for x. The good news is you can take the equation where you have x equals and substitute that y value in for there. X equals 8 minus 3 times y value of 3. So that's 8 minus 9, which is negative 1. So your final solution, written as an ordered pair, is negative 1, comma 3. That problem was a little longer using substitution. Let's see how long it is using elimination, if it's more beneficial to use it this way. I say it probably is. The whole idea behind elimination, once again, is once you add down the rows, which it looks like here, you wouldn't eliminate something, but you try to, and then you say, okay, then let's manipulate at least one of our equations. I say the bottom one would be easier, because 4 is a multiple of 2, So if I multiply the bottom by negative 2, on top this will remain the same, but on bottom everything will multiply negative 2, so we'll get negative 4x minus 12y equals negative 32. The 4x's cancel, and you're going to get 5y minus 12y, which is, once again, negative 7y, and once again you get negative 21, and y equals 3, and so on and so forth. It keeps going until you find your solution. So you can see substitution and elimination method take form, and you would get the same exact answer either way. And I hope that was helpful for systems of equations. We have more. I'll speed up. My apologies. I had no idea we did. Okay, I'll just do one each time this time as we go on. This one is already set up for substitution method. Now you do have a 1/4 in there. Oh well. There are a couple things I can do with this. I'll do substitution one of two ways. X already equals this, so I can substitute this in place of this x. And I know you might be fearing the fraction, but I'll tell you what, it's going to go away pretty quickly. 4 times 1/4 y. 4 times 1/4, taking 1/4 of 4, that's 1. 4 times 1/4 is 1. 1 times y is y. 4 times negative 1 is negative 4. So as you can see, it went away. Combine like terms. Y minus 3y is negative 2y. You still have the minus 4. Add that minus 4 over, and you'll get negative 6, so y equals 3. Substitute that 3, I guess, into this equation. Here's where you're going to get a bit of an issue. You can substitute in this equation right here, but again, that fraction's taking hold. And you'll get x equals 1/4 times 3 minus 1. So x equals 3/4 minus 1. 1 is also 4 over 4. So you can see a good reason why I want to write that, because now I have a common denominator, which is negative 1 over 4, or negative 0.25. So either those answers are good for x, and there's y. So your final solution, if I use the fraction answers instead, that's negative 1/4, comma 3. The other thing I said that I could have done with this equation is you can multiply both sides by, say, 4 to begin with, and then you'll get 4x equals y minus 4. And now you can either put this right in, because these both have 4x. I didn't talk about this with substitution. I just said get variables by itself. Not necessarily. Get a term to be represented in this equation. And here, 4x equals y minus 4, that can take place of 4x in that equation, which it did. But we still had a fraction in the end. And and also I could have used this and done elimination method by that point, because I have 4x's that are already lined up. Okay, in this one here, let's just get, I'm going to start just by adding down the list immediately, only because terms can combine, and these guys cancel. Okay. Now what I have is, look at these y's here, 3y and 3y. If I subtract 3y from both sides, they cancel, and you get 5x equals 5. You'll get x equals 1. Kind of interesting. This wasn't even a system of equations. I mean, I did use elimination, but not in the way that's kind of intended. You could have done a lot of things with this problem. I'm being different with it. That's okay. Let's take this x equals 1 equation, substitute it into one of these. Let's do the top one, I guess. So 2 times 1 plus y equals negative 2 times 1 plus 5. So 2 plus y equals negative 2 plus 5. 2 plus y equals 3. Subtract 2 from both sides, you'll get y equals 1. So x and y both equal 1. Your order pair is 1, 1. Very cool. Like I said, a lot of ways to do it. Let's save time. Let's move on. Let's solve after first rewriting it in a simpler form. So I think it just means get the left and right side to be simplified, which is fine. distribute this 3 in this first equation, and you'll get 6x minus 3 plus 12 equals 4x minus 3. Combined like terms, we'll get 6x plus 9 equals 4x minus 3. I don't even really know why they give us all this. I would have been doing this anyway. But I think there's a lot of different ways you can do it. Anyway, keep solving. Subtract 4x from both sides. Subtract 9 from both sides. You'll get 2x equals negative 12. Divide by 2, you get x equals negative 6. You can double check that answer, substitute negative 6 back in the original equation, and see if the left side equals the right side. I'm pretty sure we got that one. Okay, fractions. No one likes them, not even myself. Doesn't mean just give up on the problem. Do something about it. Because it's an equation, you can multiply both sides by anything you'd like, as long as you do it to both sides of the equation. This side has terms being divided by 7. So if I multiply both sides by 7, so 7 multiplies by every term, like so. I'll just write 7 times 2, just so you know. 7 gets multiplied by everything. Don't confuse yourself too much with this. This is 7 over 1. And more importantly, this is 7 over 7. Those cancel. The whole point of multiplying was to get rid of the fraction. We did. And in turn, these numbers just become what was on top. And you're saying, well, we can just do that? Well, sort of. What happens here, though, is this also gets multiplied by 7. So don't forget that. So 3x equals 12 when you subtract 2. When you divide by 3, you get x equals 4. There we go. So that's writing a simpler equivalent form. Does this look easier to solve than this one? Yes, for anybody. Doesn't matter who you are or how mathematically strong you are. This is always easier. Go for it. Okay, this one here is an idea of what's called cross multiplication. And I'll kind of state what it is by doing it a more difficult looking way, because someone's like, you can just cross multiply. Yeah, but I'd rather you know what cross multiplication means. Let me first show you what cross multiplication is. Taking the denominator and multiplying it by the numerator on the other side. So eventually we'll get to this. Okay, but remember what I just did with the last problem? We cleared out fractions. If I wanted to get rid of this 5 in the denominator, I have to multiply both sides by 5. But I also have an x. What if I want to get rid of the x? I'll have to multiply both sides by x. And not get rid of it, I just mean get it out of the denominator. But remember what happened with those 7s on that previous thing? X over x will cancel over here. Over here, 5 over 5 will cancel because it becomes 1. What are you left with? 5 times this quantity here and 3 times this x right here, which gives you cross multiplication. So the magic trick is multiplying straight across. The reason why is because, hey, you're actually doing math. So distribute 5 with the x and with the negative 3 and continue to solve. Subtract 3x, you'll get 2x. Add 15, you'll get 15. And x equals 15 over 2. Don't say this is no solution. That's an actual number. It's also 7.5. Either or is valid because this is an exact decimal and this is a reduced fraction. Okay, letter D. This one involves more distribution. Now, when you distribute the left side, you'll do 4x times x. That's 4x times x. Don't forget what that actually means. Minus 4x times 2, that's minus 8x. 4x times x is 4x squared. Okay. On the right side, we're going to multiply all of these terms here. 2x with 2x, 2x with negative 3, 1 with 2x, and 1 with negative 3. We'll do 4 different multiplications. 2x times 2x is 4x squared. Don't forget that x there, or the squared. 2x times negative 3 is negative 6x. 2x times 1 is 2x. And 1 times negative 3 is negative 3. If I combine like terms on the right side, we will get 4x squared minus 8x on here still. And here you will get 4x squared minus 4x minus 3. We can subtract 4x squared from both sides, and they will be gone, which is good. We don't have to deal with any x squareds. We can add 4x to this side. This will go away here. On this side, I'll have negative 4x still, and here I'll have negative 3. Divide by negative 4, you get x equals positive 3 over 4. That's also 0.75, which is an exact decimal. Either solution works.